I have a quick question. Have you ever wondered, what if the derivatives we try to solve at school are applied to real-life situations? Come on, let's try it out with the gang. So we are given this problem. An object moves along a line so that its position at any time t is equal to or greater than 0. Is given by s is equal to f of t is equal to 2t cubed minus 3 squared minus 12t plus 8, where s is measured in meters and t is measured in seconds. In this problem, we have to solve for letter A until E. Let's go!
Let's try and solve for letter A. Find the position of the object after 4 seconds. We will just have to substitute the value of the seconds into the equation. Plug in 4. So now, we have s of 4 is equal to 2 times 4 cubed minus 3 times 2 squared minus 12 times 4 plus 8. Simplify this equation to remove the exponents. Now, we have s of 4 is equal to 2 times 64 minus 3 times 16 minus 48 plus 8. Simplify everything again, leaving us with s of 4 is equal to 128 minus 48 minus 48 plus 8. Add and subtract everything. The answer for letter A is 40 meters. The position of the object after 4 seconds is at 40 meters.
Now, for letter B, we have to look for the instantaneous velocity when t is equal to 4. So, in this problem, the velocity is the derivative of the position, meaning we have to get the derivative of the equation s of t is equal to 2t cubed minus 3t squared minus 12t plus 8. We all know that to get the derivative of an equation, we must multiply the exponent to the given constant and subtract the exponent to 1. For example, on our first term here, 2t cubed, the derivative of this term is 6t squared. How? Multiply 3, which is the exponent to the constant value of 2 to get 6. Then subtract 3 by 1 to get 2. Do this on every term. We'll get velocity of t is equal to the derivative of s of t is equal to 60 squared minus 60 minus 12. Now, getting the instantaneous velocity, substitute the value of t, which is 4, to every t on our equation. So now we'll have 6 times 12 minus 6 times 4 minus 12. Simplify everything. Now we'll have 96 minus 24 minus 12. Simplify again, we'll get 60. The instantaneous velocity when t is equal to 4 is 60 meters per second.
Next up, we'll be looking for its acceleration when t is equal to 4. In this equation, acceleration is the derivative of velocity, meaning to say, we'll just have to repeat the same process we did in the previous problem. Letter B, we'll be looking for the derivative of the previous derivative, which is 60 squared minus 60 minus 12. Again, multiply the exponent to the given constant and then subtract the exponent by 1. We'll get the derivative of acceleration of t is equal to the velocity of t is equal to 12t minus 6. Then, substitute the value of t again, which is 4 to the derivative. Now, we'll have acceleration of 4 is equal to 12 times 4 minus 6. Simplify everything. If 4 is equal to 48 minus 6, subtract to get 42. The acceleration when t is equal to 4 is 42 meters per second square. Well then, what about this? What if the object is at rest? Let's analyze this. If an object is at rest, then the velocity of t is equal to 0. We'll use the second derivative in velocity, 60 squared minus 60 minus 12 is equal to 0. To solve this problem, let us divide the terms to what they have in common. We'll use the common monomial factoring method. As we can see, all of the terms are divisible by 6. So, divide everything by 6. we'll get t squared minus t minus 1. Next, we will to factor the trinomial to get its roots. The factored out of form of this equation is t minus 2 and t plus 1. Get the roots by transposing these terms. T is equal to 2 and t is equal to negative 1. Since the value of our t is greater than or equal to 0, the answer is 2. When the object is at rest, it rests for 2 seconds.
For letter E, well then, when does the object change directions? The answer to that is this. An object changes its directions when its velocity changes signs. So, just like what we solved earlier from part D, the object changes directions at or every 2 seconds.
And that is how derivatives are like in real life. That's all for today's video. See you when we see you. Bye-bye!